You ever stop and think about what makes a lemon sour, a pineapple smells so sweet, or even how a simple bar of soap actually works? I mean, they seem totally unrelated, right? Well, it turns out they share this hidden chemical connection, and today, we're going to pull back the curtain and uncover that secret. So, really, what is it? What single thread could possibly tie together the sharp tang of citrus, that amazing smell of fresh pineapple, and the cleaning power of soap? The answer, you might have guessed, isn't some kind of magic, it's chemistry. And that's really the whole secret. All of these incredibly different things are connected by just one family of molecules. And once you kind of get how they work, you'll start to see a huge part of your world, what you taste, what you smell, in a completely new light. Okay, so here's our game plan. We're going to start with the source of all things sour, these things called carboxylic acids. Then we'll see how a tiny chemical tweak transforms them into sweet-smelling esters. After that, we'll scale things way up to fats and oils, and finally, we'll reverse the whole process to figure out how soap is made. Ready? Let's dive in. All right, first up, let's talk about that tangy, sour flavor. You know, whether it's in vinegar, sour candies, or even the weird sting of an ant bite, that sensation comes from the exact same place, a group of molecules called carboxylic acids. So what in the world is a carboxylic acid? Well, it's basically any organic molecule that has this special feature attached to it, a carboxyl group. You can think of it as a specific arrangement of carbon and oxygen atoms that acts like a unique chemical signature. And believe me, this signature group is the key to everything we're talking about today. And you find these things everywhere. That sour hit from vinegar? Yep, that's ethanoic acid. The tartness in lemons and those super sour candies? That comes from citric acid. Even the sting you get from an ant's bite is caused by one, methanoic acid. They are quite literally the chemical definition of sour. And you know, that carboxyl group has a surprisingly powerful effect on a molecule. Get this. Take methane, which melts at a ridiculously cold -182 degrees Celsius. Now just add that carboxyl group, turning it into methanoic acid, and its melting point skyrockets to a +8 degrees. That huge jump happens because the group is polar, which makes the molecules stick together way more tightly. Okay, we've got sour down. Now let's see how a really simple change can create something incredibly sweet. We're now entering the world of esters, the fragrance makers. So this is the big question, right? How can you possibly take one of those sour and sometimes, let's be honest, pretty stinky carboxylic acids and turn it into the wonderful scent of a fruit? It kind of feels like alchemy, but it's just a really cool and totally predictable chemical reaction. Let's start with our before molecule, buteic acid. And to be blunt, this stuff is known for having a really potent, pretty unpleasant smell. Yeah, definitely not something you'd want in a candle. But then you have the after. With just a tiny chemical tweak, that same stinky molecule becomes methylbutanoate. And what does that smell like? Fresh pineapple. The transformation is absolutely incredible, and it all comes down to swapping just a single hydrogen atom. That's it. The chemical process that makes this magic happen is called esterification. Basically, you take a carboxylic acid, you react it with an alcohol, and you end up with two things, a sweet-smelling molecule called an ester and a little bit of water. It's a classic, straightforward reaction. And this one reaction is responsible for so many of the fruit scents we know and love. The smell of apricots? That's an ester called pentylbutanoate. Cherries? That's ethylbenzoate. And that unmistakable aroma of oranges? You guessed it, it's another ester, octyl ethanoate. Nature is basically a master chemist, creating a whole library of amazing scents using this one simple trick. So we've gone from sour acids to sweet esters. Now let's scale things up. I mean, way up. Because it turns out the fats and oils that are in our food, they're really just giant versions of the fragrant esters we were just talking about. And here is the absolute key connection. Fats and oils aren't some totally new type of molecule. Nope. They are simply massive esters, and they have a special name, triglycerides. They're built on the exact same chemical principles we just saw, just with much, much longer building blocks. Okay, let's break that down. A triglyceride is formed from two main parts. The alcohol part is a molecule called glycerol. And instead of a small carboxylic acid, it uses three really long-chain carboxylic acids, which we just call fatty acids.
So one alcohol plus 3 fatty acids combine to make one giant ester, a triglyceride. Simple as that.
And this explains why some fats are solid, like butter, while others are liquid, like olive oil. It's all about shape. Saturated fatty acids have these straight, flexible chains that can pack together really neatly and tightly. This creates strong attractions that make them solid. But unsaturated fatty acids have these kinks or bends in their chains. These kinks physically prevent the molecules from packing closely together. That means weaker attractions, and the result is a liquid at room temperature. It really is all about the molecular geometry.
Okay, we've built our way up from acids to small esters to the giant esters we call fats. Now for our final act, we are going to bring this whole story full circle by breaking those fats right back down to create soap.
The name for this process is saponification, and it's basically the reverse of esterification. You take a fat or an oil, that triglyceride, and you heat it up with a strong base. This chemical reaction breaks the ester bonds, splitting that giant molecule apart. Here's the play-by-play. You start with your fat or oil. You add a strong base, like lye. Then you apply heat to get the reaction going, which breaks those ester links apart. And what you're left with are the original building blocks, just slightly changed. You get the glycerol alcohol back, and you get the fatty acids back. But now they're in the form of a salt. And that salt, well, that is soap. So there you have it. We've traveled from the taste of a lemon, to the smell of a pineapple, to the texture of butter, all the way to a simple bar of soap. And we did it all just by following the trail of one single chemical family. And that really is the heart of this whole thing, isn't it? The carboxylic acids and their derivatives, the esters, are literally writing the chemical language of our world. They're responsible for an incredible range of sensations and materials that we all interact with every single day. You know, the biggest takeaway from all of this is just how powerful tiny changes at the molecular level can be. Swapping a single atom turns a nasty odor into a sweet perfume. Adding one little kink to a chain turns a solid fat into a liquid oil. It's just a beautiful reminder that the entire world we experience is built on these tiny, elegant rules of chemistry. It really makes you wonder, doesn't it? If this one chemical family can connect taste and smell and even soap, what other parts of your daily life are just sitting there, waiting to be re-explained by the simple, powerful logic of chemistry?